Good. Hello, everyone. I see we have a few people online as well. It's nice. It's good to be here. Thank you, Anai, for the introduction. Thank you for having me. I'm not from Seattle, and I'm not from Cambridge. I'm originally from Prague, where I grew up, and then I moved to UK for education. Which means that if my expression is some of the mix of the British cynicism and the Czech frowniness, don't be alarmed. It's an artifact of my upbringing, and from my understanding, quite a freaky one for American context. But I don't know if any of you are American, in fact, so it doesn't matter. So let's talk about the work. So this wouldn't be possible without my co-authors. I've talked briefly about them, so it's Naomi, John, Adina, and Ryan. I should probably update the affiliations because I think that some of theirs have changed in the meantime, but yeah, it wouldn't be possible without them. So big thanks to them. And while not in person, they're here in spirit, I'm sure. So why is compositionality important? Let's dive in. Well, we want neural networks that generalize compositionality. This is a big discussion topic. Usually it's not maybe talked about in terms of compositionality. It's talked maybe in terms of alignment, but in many ways these things are interlinked. So if you're interested in pursuing neural networks that do behave or generalize at least like humans, then you are interested in compositionality. And compositionality might in fact be a way towards robust neural models that are reliable, that we can reasonably predict how will they behave in different contexts. So this, especially now if we'll talk about alignment, becomes an interesting and important topic. And the question is, can we do this from text alone? Now, to contextualize in what's now, I guess, all the rage, even when people are exploring things like prompting methods, people do think about generalizability, and they particularly talk about scan language, and we'll come back to these later on. So if compositionality is important, let's maybe have a look at what does compositionality mean. Well, one definition, a popular mathematical definition, comes from Richard Montague, a very interesting character. If you have not had a chance to look up his Wikipedia, please do. It's shocking. And the man himself is quite shocking too. At least in his confidence, he is here from Parque. He sits down one day and he proceeds to do something which he regards and continues to regard as rather easy and not very important, to analyze ordinary language, i.e. that's his view on linguistics and NLP. So Richard here comes up with the definition.
The screen is a bit, if people might not see it, and if you can.
Yeah, good point. Let me go which way?
Not this.
Yeah. Thanks.
Oh, that's better.
Also, feel free to ask questions and shout along. Yeah.
What is the difference between compositionality and generalization? Like, can you use it interchangeably, or?
Well, we're talking about specifically composing meaning as a method of generalization. So I would say a subset of that. Yeah. Good question. So what does compositionality mean to Richard Montague? What is this the mathematical definition he comes with? Well, he has two pieces of knowledge for us. One, there's no important theoretical difference between natural languages and the artificial languages of logicians. That's one of his famous claims. And second, which is more specific to the compositionality, is an interpretation of Montague, in fact, which is that syntax is in algebra, semantics is in algebra, and meaning is a homomorphism between them. So this is what we're going to be building with. We take these existing kind of famous big ideas about what compositionality would look like, specifically that it is this homomorphism, and we'll try to do something with it. So let's have a look first at what the data sets that are used currently in order to explore compositionality. What do they look like? They are handcrafted data sets typically. And the most famous one, the one that you saw cited in that paper from a couple of days ago, is citing scan language. Scan, we'll have a look at it in a bit, has a bunch of follow-up, like grounded scan, and people have played with it differently, tried to change it, but fundamentally it's a handcrafted compositionality data set. It looks something like this.
It was synthetically created, no?
Yes.
So, okay, so handcrafted.
The grammar is designed.
Yeah.
And it's a single data set, single grammar, single set of translations. It's finite. So, for instance, it's very simple as well. That's kind of the beauty.
Yeah, but it's not that like humans created.
It's not exactly. Yeah, you're right. Yeah,
it's synthetic in that sense.
It's synthetic. But we'll come back to distinction of, I guess, synthetic and sort of human crafted, and synthetic and sampled, which is what.
English also humans created, right? English was also created by humans.
No, yeah, but this was like
this was
it's
kind of
not
like
like from natural language.
It is not from natural language. It's it's a made-up language, and it looks something like this.
Also, it's not that people were thinking how to create a sentence. They created the grammar and they created the sentences or the artificial sentences out of that.
Yes. So it looks a bit like this. On the left, you have the input, which is jump. You translate to jump. Jump left becomes L turn jump. Turn left twice, L turn, L turn. It's a sequence-to-sequence translation task, effectively, that you do over the scan data set. And that's what it is. That's what we currently had with respect to benchmarking compositionality. And these data sets are great for a few reasons. I mean, they are you can think about the problem and then you can kind of design it, what you want the data set to do. You have control over the content, and yeah, they give you this ability to examine one particular thing. So those are the upsides, but they also have downsides. They are time consuming to create if you want to do something a bit more complex. If you don't want to do something more complex, then you will likely have a single example of an entire class of languages, like in the case of scan. And it's very hard to link in some formal way the learnability of that particular instance that is generated by this artificial data set, human created data set, to some general aspect of language. So those two things tend to be a bit disconnected. And unsatisfying. So how about we don't handcraft them? We don't like sit down and design how jump will turn into capitalized jump. How do we automate it? Well, in order to do that, we need some sort of formalism. And in order for it to be better than for humans to do it, we need a formalism that is mathematically well studied. We need something that's provably learnable, that would be ideally familiar to NLP practitioners, and best of all, if it could also generalize previous work on compositionality like scan, then that would give us an improvement, a better tool to examine compositionality through these data sets. So let's go back to Montague. According to Montague, the key thing is the homomorphism. So let's talk a little bit about what homomorphism is. It's a structure-preserving function. Specifically, it preserves monoidal structure. Let's have a look at what is a monoid. I should say a small audience. Are you all familiar and bored with homomorphism and monoids, or should I? Let's go through it then. So what the heck is a monoid? It's a simple algebraic structure. So formal definition, it's a set A equipped with the operator bullet with following three properties. It's closed, it's associative, and it has unique identity element. That's what a monoid is. So here's an example of a monoid, the free monoid. So you can see that it's just a simple alphabet. where the operation is concatenation, and then we can check whether it satisfies our definition of free monoid. Closure, yes, but by definition. Associativity, yes, and identity element, epsilon, which is you can think of it as a, let's say, empty string, in a special string in an alphabet.
What does this star represent?
The star is a cleaning closure. It means all the possible permutations within that set.
I see.
Yeah, so it's like having a alphabet of set is an alphabet, then cleaning closure of that set would be all the possible permutations of that. And that's basically the closure as well. So if we define our monoid as a cleaning closure over an alphabet, it will satisfy the closure requirement. Okay, so what is monoidal homomorphism? A bit of a mouthful, but more than that, it's basically a homomorphism between two monoids. So we have two monoids. You can see them A, B, defined there. They have the same identity element, epsilon. And if we have a function f between A and B, it is homomorphism if, and there are only two requirements, if you put the identity element in the function returns identity element, so that's requirement 1, and requirement 2, if you input the X operator Y, so this would be like, let's say you're concatenating two words, and you put it in the function, the outcome will be the same as concatenating the outputs of the processing of the function over the word. So hello, how are you, type of thing, as a single thing, as opposed to separate thing and concatenate it. So those are the requirements. So it's very simple, and this is the definition. This is now you know what Montague talks about when he talks about compositionality. So how does it relate? Yeah.
So are we talking about compositionality of any language, or is this some specific crafted synthetic language that we have?
Yeah. Let's go back to scan to flesh it out a little bit. So what does this mean? This is some sort of translation between words on the left,
Right.
and semantic states on the right.
Why would you not say words on the right?
Because that's the assumption that you're making in scan language. You kind of say, okay, well, there's a transduction happening between this interface of language and the semantic space, and they are interlinked, but they have different operators. In case of scan, they just get kind of turned around. So jump left semantically becomes L turn jump. And the intuition kind of for that is that imagine that you're controlling like an RC car and you're giving it instructions. So the idea of scan is that you issue the command, and then the command gets translated into what is the instruction that is meaningful within the state of the RC car, which is the capitalized version here. It's kind of simplistic, but that's roughly the intuition there.
And it's very limited.
Yeah, it's. And so now you have kind of this background of, okay, what people do in terms of scan, and you're right, there's this sort of, okay, so how does it relate to compositionality? Now you have a definition of what compositionality would look like mathematically. Specifically, it's this homomorphism, and we're going to try to bring them together in some way. So that's where we are. In order to bring them together, we need to have a look at subsequential finite-state transducers. I don't know how familiar you are with automata theory, but just quickly, a transducer, well, you can define it like that, but effectively, you have input and output. So you have state, input, and output, So if you input A, the transducer returns B. If you input B, the transducer returns A. That's what this FSST, SFST, sequential finite state transducer, encodes. That's the structure it encodes. That's what it's for. So, and it's deterministic, crucially. So let's see, maybe, can we link the idea of homomorphism to the idea of these SFSTs? And can we have then this machine that encodes homomorphism and thereby would somehow capture aspects of compositionality? Well, we can check if a homomorphism, if SFSTs satisfy homomorphism. So we have our checks, and what we find is that for a single state SFST, it is indeed a homomorphism that is encoded. So how do we know that? Well, we have the two requirements, right? Nothing in, nothing out. That's the first requirement. So if you don't do, if there's no input, no output, that's satisfied. If you input AB, it should be the same as inputting A and then having another go and inputting B. So FAB would be BA would be returned, right? And if you do them individually, you get the same thing. So concatenating them returns the same thing. Does it make sense? Is it? Okay. So in a simple situation, this SFST satisfies Montague's definition of compositionality. What it produces is, or what it captures rather, is the compositional relationship, is the homomorphism. So this is the kind of the initial idea. Okay, so maybe we can use these SFSTs to sample them, and then generate whole data sets that we can sample completely randomly, and we can do thousands of them, unbounded number, and we can then explore based on these different aspects of an SFST, these precise controllable points. What about these points determines whether a neural network can generalize over them? That's kind of the idea. But there's a problem. If you increase the number of states to 2, you lose the homomorphism. You can check. So input AA, we start from 0, so it's BA. Input A is B, so BA is not equal to BB. Do you see why? You start from 0, you get B. If you run it again, then you get B. If you input A, you get B, and then you get A. You're moving through the states. That's how it works visually. Yeah? The input moves you from one state to another in a two-state scenario. So you don't have homomorphism. So that's the problem. You see it? Okay. So this is a problem. So if we want to use something like these formal languages, if we want to use these automata, if we use the automata theory, these transducers, in order to link compositionality to formal language theory, we need to overcome this. Because if we just sample them, we lose that link. The link is the homomorphism. The homomorphism is the definition of compositionality we are going with. It's one definition. There are other definitions, but it's the one we want to link because it's one of the famous ones.
But can you elaborate? So this is like one example, right? Like if you had changed the state here, not the state that.
Yeah, proof by exception in this case that not all will satisfy.
Yeah, not all of them.
Yeah,
but there still could be.
There still could be. Yeah.
So like, what? I think I'm missing something from like.
Well, if you want to sample randomly these structures, right?
Why do you want to sample them randomly?
Because you want to create a data set like scan,
Okay.
And you want to make sure that that data set is better than scan, and you want to do it on two levels. On one level, you want to make sure that that data set is, you can sample as many as you like from data sets. And B, you want to make sure that it is actually linked to a theory of composition, a mathematical definition.
Why not sample and check if it does satisfy?
Sure, you could do that. To come up, that would be one solution. We have a better solution,
okay,
where we can use them. Yeah, absolutely. As long as you see the problem, then then that's the important bit. Yeah, and yeah, I guess you could write write code to check all your samples and make sure that there's nothing like this. But imagine that you want to sample really big ones. Let's say that you want them to have hundreds of states and thousands of translations between them. It becomes messy. Maybe not the optimal way of going about it, but yeah, it's possible. We had a different idea, which was okay. Well, maybe that's not a problem because we can just change the representation slightly. We can kind of lift the monoid into a matrix, and that will satisfy the requirement. So what do we do here? Well, you can represent this as a matrix. 0 state, nothing. 0 state, first state, return B. 0 state, first state to 0 state, return A. And 0 to 0, return null. Do you see how this can be encoded through the matrix?
What are the zeros?
So think of them that these are basically indexing the positions here, right? So if you go from 0 to 1, you get B in return. Yeah, and if you stay in 0 to 0, you get nothing. It's not a valid move, in fact, in this SFST. But and same, if you go from first state to 0 state, you get A in return. That's what we are encoding here.
In this, I'm calling it ST.
SFST, yes. Subsequential finite-state transducers. Subsequential just means that they're deterministic.
So in this case, FAB cannot be an input. Right?
In this case, you can't. Yeah, this SFST only takes A as an input.
It cannot take.
It doesn't. Yeah, it can't take anything but A. The left side of the bracket, that's the input. The right side is the output. And yeah, so if there was B here, then you could accept B from 1 to 0. So this would would still be A because this is encoding the outputs of the SFSTs. States encoded in a matrix. This is how you can represent the SFST as a matrix. That's really the idea. And then what's nice about it is that if we do this matrix multiplication over these matrices with symbols, we can come up, so what would be the result of this matrix multiplication? Well, it would be what you see here on the right, which actually encodes the correct information about the translation, which actually is a homomorphism. So each translation is encoded as a matrix, and then transition between the translations is a matrix multiplication. That's what we do here. That's how we translate the problem into kind of this matrix representation. So this encodes the same thing as the SFST, just in a slightly different way.
We have a question from Ashish.
Yes.
I had just like a basic question here. So I thought we were dealing with monoids that have just one operation, and matrix multiplication you need two operations, like a group. What does multiplication mean here? Do we have the plus operator and the concatenation?
Yeah, you're right. So we are doing this multiplication concatenation as a single step. Yeah. That's basically what's happening. Yeah, we define the operator as this multiplication over the
I
state.
see. Okay, thanks.
Yeah. So just to put it together, we're gonna get back to that question when we check whether it's a homomorphism. But now you see that we can do this nice translation where we satisfy the homomorphism, so we get this representation of the SFST as this matrix, and we can now check, does it satisfy the homomorphism? Well, if we are turning these, if our functions kind of translation into these matrices, then we do have a homomorphism. That's what we are binding after, and we can check it. If we apply AA, then we get the same output as if we apply A twice, as long as the operator is this matrix multiplication over the strings.
Sorry, can I ask one more clarification here?
Yeah.
So let's assume this monoid, I think this goes to some other questions somebody was asking. Let's say this also allowed a transition on B, like from 0 state, you read a B and you write a B. Similarly, on 1 also, you read a B, write a B. Is it correct? And then this matrix will have, I guess there will be the B matrix that will have a certain, also matrices for when you read A are different from the matrices that when you read B. I guess what I'm trying to get at is that do these matrices always have zeros so that you don't get into this issue of, when you multiply them, you don't have a concatenation and a sum, like you never get AA plus AB or something like that. Is that true by design?
It should be true by design by the definition of the SFST, but I'm not entirely sure exactly what the reason for it is. But yeah, in practice, it is always like this, and it's by how we sample the SFSTs. But it's kind of it's how they are how they are encoded in the matrices. Yeah, no, you're right.
Thanks.
Yeah, sorry. I on top of my head, I'm not entirely sure exactly how.
And I think it does work out because you have, I think the transition, because it's a deterministic automaton, there'll never be in a row. I think you'll see only one entry fill, something like that.
There should be only one per row. Yeah. We ensure that in sampling. I know that for certain, but I also wonder if that's because we are constraining. I think that's only because we are constraining it in order to be deterministic, rather than we are hacking it in order to get around this problem. That's my hope here. Yeah.
Yeah, no, I think it is true. Determinism gives you this, so that when you do a matrix multiplication, you basically get just one term, not a sum of like 3 terms or something. Cool, thanks.
Thank you. So let's go back to Montague. So again, we covered this. What does compositionally mean? Well, according to Montague, as interpreted by Janssen, it's a homomorphism between algebra and semantics. Sorry, between syntax and semantics. Homomorphism in algebra. And there's no important theoretical difference between natural languages and the artificial languages of logicians. So how do we use this to evaluate neural networks? Well, we have these handcrafted compositionality dataset like SCAN, but we want to overcome these downsides of them. We want to make sure that we can kind of create them instantaneously. We want to make sure that we can sample over different class of languages, and we want to make sure that we can attribute to some precise aspect of language. And we get all of these with the SFSTs, right? We know the different parameters that we can toggle. That's the definition of the SFST. We can therefore sample unboundedly many SFSTs and generate as many data sets of as much length or size as we like, and we can do that kind of instantly. So how do we go about it? Well, we sample matrix. We populate it with 0 and 1. At most, a single non-zero entity in every row. Ashish have it there on slide. And one indicate where transition from one state to another happens. And then we minimize them to ensure that they're actually unique. So we ensure that they encode different SFSTs. And then all we do in order to generate a data set, we just walk through the SFST for the number of steps we would like to land. So we assume that every state is a finite state. So specifically, we generate 2,800 unique SFSTs, and then we generate the data sets from these that contain 20 to 40,000 unique input-output pairs. We split 80-20 to then train neural models. But the point here is, well, you can search within the space now by the parameters wherever you like. We just did our experiments within certain space that we thought was interesting, but fundamentally there's no bound on it, and that's the point.
The Schmid-Huber did it in the 80s or something?
We used LSTMs because the claims of cognitive plausibility, so we focused on them, especially for a translation task that can give us a better intuition about compositionality. But yeah, you can train whatever model you want. We did LSTMs, sequence-to-sequence models, and we find a couple of things. We find that there's a minimum transition coverage of 400 samples here.
Do you have more than 2 transitions? How many transitions can you have at most?
Yeah, well, so it's a good question. So we have constrained it. We did it by number of states, and I think if we wanted to redo it, we would probably want to sample by number of transitions, because it seems that the transitions, and particularly the number of examples per transitions, are what determines the learnability. We did it by number of states because we knew the number of states of scan, which we wanted to compare against. So we find this drop-off. The drop-off is a factor of the number of transitions. How many times you see a transition?
What's the task exactly?
The task is a sequence-to-sequence modeling task where the inputs are the input alphabet and the outputs are the output alphabet, and the translation between the transduction is encoded by the SFST from which we've sampled, and then we walk through the generated data set. So finally, we look at scan as an SFST.
Another question. Did you control for the number of examples you shown? Or like how graphs of like number of examples versus performance?
Yes. So the when I say 400 samples, I mean 400 times in the data set where the model goes from 0 to 1. Let's say in this example. Is that what you mean?
No, like so in the previous slides, I think you showed, yeah, you have different 2,800 different SFSTs, right? And then for each one of them, you have 20 to 40,000 pairs sampled from each SFST, and then you train a model on each one of them separately.
Yeah.
So you have like 20,000 times 2,800 different data sets.
No, we have we trained 2,800 models. Well, we trained more. I think we hyperparameter optimized them as well. But and each of these data sets is comprising of 20,000.
Yeah, that's what. So you have like 2,800 different datasets and models.
Yes.
And each model
Yes.
has 20. And for each model, or for each dataset, did you train like at least one model, right? But did you also try to teach or like at least learn, check the learning curve of like how many training example? So it can be like a graph of like how many training examples versus performance, right?
Yeah.
Do more training example make the model better, basically?
Well, we kind of find, yeah. So we
So like
don't-
what I'm saying, is maybe 20,000 example is not enough for some of those.
Yes. So okay, yeah. It's a good question. Absolutely. So you see the purple line here
Mhm.
is the 40K data sets. The blue one is the 20K. So there's a shift, but fundamentally it's the same thing.
Yeah, but maybe if you use like 1 million example,
Then it might suddenly be conscious, yeah. But like, yeah, we only do it in the spaces we have, yeah, which are fairly. You're absolutely right. Yeah, they are fairly small. We do hyperparameter optimize them, so we run a number of models on each of them, and yeah, we do 2,800 of them. We do it in roughly the same space of state that scan has, in order to kind of draw some comparisons there. But yeah, you could sample million plus size of a data set and see that it might be, if you're just in emergent properties, then you might want to do exactly that to see whether it's just a matter of scale. Also, these are all trained from scratch, right? So there's no, they have no, and the data has no like correspondent to semantics of humans, or anything like that. It's just numbers.
Also, if you sample, you might get duplicate examples, or do you control for that? And then if you also split it randomly, you might get contamination between the train and test. Is it something that you test for?
So we ensure that the SFSTs are unique. So the structure, the transductions that is
but this is for each different class. But then from each SFST, you sample
the walks
right?
through.
And the walks might, if you
Yes.
sample them, they might be maybe repetitive ones, and then you might. So it's also a problem in terms of like comparing different SFSTs, but also it might be that there is contamination between the training and the test set.
Yeah, you're absolutely right. We ensure that they are unique.
Okay.
So no two are the same. But
So
it will
continue
be
sampling until you get 20,000.
Sorry.
So you continue sampling until you get 20,000.
We sample until we get 20,000 and ensure that each path is different from all the paths that we've already sampled.
Okay.
That's the yeah. Which becomes, so the smaller the SFST, the more challenging this becomes, right? There's kind of a limit on this because good. So back to scan. What would scan look like? SFST. Now you know like what we are talking about. So let's have a look at the prior work that we are inspired by, and let's see what that would be in terms of SFST. Well, scan would be quite a big SFST. In fact, we estimate that it would have, we calculate it would have over nearly 8,000 states. And that's, we'll come back to that. So our minimum transition coverage is broken by scan. What we've observed empirically, right, is 400 samples. Scan doesn't get 400 samples. So how come that you can learn it perfectly? That's kind of what we get surprised by. So why would that be? Well, it's because it's generated by a grammar, and you can cast the grammar as a subsequential finite-state transducer. It's a finite grammar, so you can twist it like we did into the SFST, but really there's a lot of these blocks within the SFST which encode effectively the same thing. If you swap jump for run in the grammar of scan, you get exactly the same structure, just with different words. And clearly, the neural network is capable of leveraging that, push down the transition coverage requirement. Ours are truly random, right? So these structures, they don't really emerge because it's not what we sample for. And it seems like these structures are leveraged by the models. We hypothesize there's a native complexity metric built into SFSTs, which is their size, but it's not the native complexity metric of the neural network under consideration. And it's not a native complexity metric of scan either, because you can represent scan in a more succinct manner, not with SFST. Let's say with push-down automaton transducer, which is what we would like to do in future work. So we have this method that the primary thing about it is that there's a connection, formal connection between, okay, what does compositionality mean? How is it defined mathematically? And how would that look like? What would be one way of looking at it in terms of formal language theory? And that's what we were after primarily, and that's the primary contribution of the work. But on the empirical side, our finding of 400 transitions, it's not the whole story, clearly. It's not really answering the question of what makes a network generalized or not. In order to access that, what would make sense to do, perhaps, is to go up the Chomsky hierarchy to link the homomorphism further in the hierarchy, maintaining that connection and sampling from there to see whether we can find different parameters within these models, within these transducers, but more complex ones perhaps, that actually are a strong indicator of the ability to generalize models, that are the native complexity metric, perhaps of a neural network, that could link the formal language theory to compositionality in a more satisfying way. And that's it. Yeah, good time.
If you go one slide back.
Yeah.
For the second to last point. So just I'm trying to understand if I understand correctly. So you're suggesting that you need to have an automata that is able to predict how easy or hard it is to learn a task?
I would like to have an automata, a transducer, which is the translation version of the automaton, that we can pin down an attribute of that is a very strong predictor, for generalizability of the neural network. And in a way, we failed in this work because we have not found that as a universal thing. We found it for this relationship between neural networks and SFSTs. We found this complexity metric of the number of translations, structures and transitions, but that is not really the complexity metric of the neural network. It's a complexity metric of the SFSTs. And we would like to find one which is linked to the automaton, the transducer, rather than that links the transducer to the neural network rather than just tells us about the transducer.
So I might have missed the model of transformer you used here. What kind of attention is it? Causal, like Ligoder only, or is it?
It's an LSTM with attention.
Transformer.
Yes, but it does have so there's a cross attention, of course, happening on the decoder side to the encoder. So it does cross attend to its full context during decoding. But yeah.
Why did you decide to go with an LSTM?
I don't quite remember, but at some point we've just went with that, and I think that because we were running so many experiments, so primary thing was a bunch of the colleagues on the paper, linguistics background, they were interested in the cognitively plausible side of it, and the work at the time when we started it, a lot of it was looking at how LSTMs are better at these tasks. So we thought, okay, that's a sensible point to start, and then we never got around running a transformer on it. But
Did you try also?
no, but but it should be very easy to run.
Easy to run, but I would predict it will not do well still.
It should do worse. It would be
unless you give it examples where it like writes down some helper things like intermediate states in the training. So then maybe there is a chance.
Oh, so that you provide it with information about the
Like
states.
it's an thought style thing. So the way it solves it is via writing down. Like, here's what I output, and I move to the state, output the state, and then it can.
Well, yeah. So okay, but that's an entirely different setting as well, because that would be using GPT-4 and seeing whether it can learn it, which is a nice way to wrapping it back to what I was talking about. Now, people are interested in this question: can large language model reason? And the difficulty, one of the difficulties that we are facing is, well, you can't really, it's very hard to benchmark it on an existing data set because it has seen everything. So the memorization versus reasoning discussion kind of gets dissolved there always. Artificial data sets, if they are done well, they could be a way forward in that respect. So one could use something like this to explore it, exactly. And yeah, then see whether chain of thought prompting is a navigation in some sort of subspace of information within the knowledge, whether it memorizes better or whether it induces actual step-by-step things, stuff like that. And that is exactly the discussion that one could then engage with from a different methodology perspective.
Another related question. So, I guess what we are testing here is learnability. Can you train it with?
Yes,
example?
absolutely. Yeah.
Do you have an intuition of whether it should be expressible? Like, should one be able to hand code an LSTM that solves each?
Hand code?
Well, figure out the weight. So, like, do they exist weight? I suppose that can be learned. If somebody were to give you Oracle weights, is it a solvable task?
Well,
I should use the word representable.
So our empirical results definitely are yes, right? It seems to be just a matter of giving it sufficient number of transitions.
It does go down.
It does go down. It does go down as you go further up the states. So the number of states is a proxy for the transition coverage. And if we were to do it again, we would focus on transition coverage of states. But this drop-off is from about, well, consider the purple line, from 29 states onwards, you stop having the number of samples sufficient for the network to learn the transition. But up until that point, it's got 400 plus, so it learns it and it doesn't struggle. The question is whether on extremely long context, and it would be the interesting difference between transformer and LSTM, of course. It would be a natural place to look at. But yeah, it's not that complicated of a structure that is encoded, and I don't know of any related work where people have particularly focused on whether neural models are capable of learning SFSTs and what are the requirements. So basically, this is the study, as far as I know. So yeah, in theory, I have loose understanding of that. In theory, everything is possible with the models. So it's on the expressibility side, on the learnability purely. And yeah, that's what we got.
How does it connect to natural language?
Yes. Where do we have them? So two Montague ideas that we are taking. Second Montague idea, no important theoretical difference between natural languages and the artificial languages of logicians.
Cool, you can say that.
So I think this is a really interesting question. Is there one? Is there not one? This is one of the ideas that there isn't one. If you accept that, then this is one of the paths you can go down. And I think the linguists have explored formal language artificial languages historically, so it's not a new idea or niche idea. It's maybe less fashionable nowadays, but I wouldn't dismiss it myself outright. I don't know. I think it's a good question.
I guess that word theoretical is important there. Practically, it is.
Yeah, absolutely. Yeah. Yeah. And like there are some, I mentioned that there are some natural semantic structures that one would like to focus on in particular, and we have no notion of that here, right? It's all just kind of numbers with no meaning that we are translating to. In reality, the model would be would have probably more information from the individual words. Or
If you can say something, if you do an experiment where you pre-train a model and then train on this data set, and the difference between like another baseline, which I'm not sure what the right baseline is, because random initialized model is probably not that, but maybe it's something else, like another kind of language, which maybe doesn't follow any structure. Do you think this kind of experiment could help answer this question?
Yeah,
related to language.
I think there are two things to look at, which is the Chomsky hierarchy, and see whether the lower level language pre-training on lower level can improve generalization on the upper level. That could be an interesting. It's a relative sort of experiment there, but it could give us some intuitions about how do these artificial languages relate to human languages in some way. What would be the relationship there? And then on the sort of more horizontal level, you could see how pre-training within the same class could affect it. I think both could give you some intuitions about what is happening when it comes to natural language. But yeah, of course. I guess the kind of the most straightforward experiment is to go and see whether we can prompt an LLM to deal with these things. How well does it perform, and what are the parameters of an SFST that affect the prompting paradigm or in context learning paradigm of an extremely large model, and that could give us the information from the other side. Let me know if you're interested in that, of course.
One more question.
Sure.
So the structure that I guess from here you motivated syntax to semantics as a homomorphism and used a simple structure associated.
Yeah.
Syntax in language is not associated.
Yes.
So have you thought about how this will change or how you might extend it to richer structures?
Yeah. So the natural or the intuitive direction is to go up the Chomsky hierarchy in terms of the automata theory, so stay within there. But ideally, one would want to come up with something else. But it seems quite hard to do so, at least if linguistics is anything to go by. Ideas are hard to come by in that space, and since we are still considering Chomsky work from a long time ago on this, it's a difficult problem, and it would be fantastic to see some work there. But here's to hoping.
There's no more questions. That's right. Joseph,
Thanks. Thank you.